Hi Mindsetters, I'm Megan and welcome grade 10s to today's science show. Today we have special revision lessons on classifying matter prepared especially for you. We'll be selecting highlights from the lessons shown early in the term to help you revise for your end of term test. You can download the notes for today's show on learnextra.co.za/live.
Hi everyone, welcome back. What we've got set up here is a circuit board with some batteries and some conducting wires. And what I've got is I'm just going to connect up here, and do you see that little light bulb glowing? Okay, it's there. I've just got some loose connections there. You see that glowing? And so what we can see here is that this power source is providing an electrical current, causing an electrical current to flow through, and it's being transferred through these copper conducting wires. So, first thing, copper conducting wires are able to conduct an electric current. So, that's the first one. Now what we're going to do is test a few more things. Maybe this iron nail, piece of candle wax, some stocking, piece of wood, and what we're going to do is observe if these things will enable us to see some electrical conduction. So I'm going to get this candle wax. Do you see a light going? No, certainly not. Candle wax is not a good conductor of an electric current. Let's move that one away. Let's try the nail. So I'm touching it to that side. Get a connection? Yes, definitely there's an electric current that is passing through that iron nail. Even if I move it across here, there we have the connection, and it's allowing the light bulb to glow, which means the current is certainly passing through. So the iron nail, yes. What about the stocking? An interesting one. I'm sure you haven't done a stocking before. So let's see, I've just wrapped it around that side, and we're going to connect it there. Does it allow an electric current to pass through? Oh dear, dropping off. No, I don't see that light bulb glowing in the slightest. Definitely not conducting electricity. So the iron nail did, the stocking does not. What about some wood? Electric current? Definitely not. The light bulb does not glow, so it's not a good conductor of electricity. Let's go and report back to our table, because I've got a couple of these things jotted down. If you come across with me, we are testing electrical conductivity. We've got a battery with a light bulb using conducting wires. When the circuit is closed, the light bulb glows, and we are testing different materials. So let's have a look. What substances did we have? We had the copper wire, observation, the light bulb glows. Okay, and the next one we had was the iron nail. And what did you notice with the iron nail? Again, the light bulb glows. So yes, it's a good electrical conductor. And if I go a little bit further down, what were some of the other things that we said? We did wood. No. Current. Or better yet, our observation was no light bulb glowing. The other things that didn't work, the wood didn't work. What else? The stocking, the candle wax, the wax. There were quite a few things that didn't work. So electrical conductivity is allowing an electric current to pass through it. Let's go to the next one and let's see if we've got any more things to investigate. Well, here they're asking us to test some magnetic properties. Okay, properties that would be attracted, some substances that would be attracted to a magnetic field or would be attracted or repelled, for that matter, influenced by a magnetic field. So I've got a magnet, and we're going to use that magnet to test which substances are attracted or repelled by that. So I've got a number of things, and we'll come and jot them down in our table in a moment. Won't you come across with me to have a look at some more? Ty, over to you while I get set up.
Okay, so I'm seeing a lot of people posting here. I just want to say what up to Oscar Mwila. My bad, dude. Like, I'm horrible. Like, if you've been on before, you know I butcher people's names constantly. Subusiso, Lesejo, Amir, I want to say thanks for you guys posting on the page. Keep on posting, and everyone else out there, keep on posting. Let us know what you guys are thinking, if you're lost and if you need help. But for now, we're going to get back to these experiments. Let's see.
Thanks, Ty. So in my right hand here, I've got a magnet, and if you can look closely, there's a compass, and I'm just moving this magnet around the compass, and you can see that dial moving quite significantly. Okay. Let's see what things are attracted by this magnet. So, what have we got? This piece of wood. Certainly no attraction there. What about this little piece of glass? No, nothing there. What about the plastic? Nothing. This ruler, nothing. Oh, that's interesting. Aren't most metals magnetic? No, they're not. Most metals are not magnetic. Only those three: iron and cobalt and nickel. They are all next to each other on the periodic table, so it's very easy to remember them. Have a look at this one. Oh, that's certainly a nice magnetic pull that we just had there. It's going to take a lot of energy to take it off. This is a piece of steel. It's actually used as a piece of welding equipment that could be melted and used. Steel is an alloy, which is actually a mixture of metals. So what they would do is they would heat up the metals, make them melt, and when they've got them to that melting point, they're liquids, they can be mixed together, and then it's got properties of both or a number of different metals that it's composed of. So they're not chemically bonded, but they're just melted and then added together. So it's an alloy is a mixture of metals when they are heated to liquid and then added together, and they have the individual properties of both. So of both or a number of the various properties. So this is some steel, which has got iron in it, and iron, we know, is certainly attracted by a magnetic field or influenced by a magnetic field. Let's go through this little piece of rubber bung, nothing there. The candle wax, nothing. This is also probably an alloy. This outer section it looks like a speaker to me, and it's certainly influenced by that magnetic field. So once again, come and have a look closely at the compass. And as I move this magnet around, you should be able to see that compass needle that is deflected significantly by the changing magnetic field. Let's go and jot down some of our observations. So back to the board. And I didn't test the iron nail, and I want to do that quickly. So let's grab the compass. Very strongly attracted, and will take a lot of energy to pull that apart. So the iron nail I'll write down first. The iron nail, and I'm just going to write yes, it was attracted. Oopsie, attracted. What else did we have? Wood. No. What else did we have? Other metals. Some metallic objects. And I think it was an aluminium. Rod? No, certainly we're not. It's only those three that I mentioned. Steel, which is an alloy of iron with other things, so that certainly is going to be have the properties of the iron, which will be magnetic properties as well. What else did we test? The rubber bung. I'll just add them in here with the wood, the rubber. We had quite a number of them. Plastic, all of those. I'm running out of space. Let me write this somewhere else. These were not. Let's even just add the plastic or glass. All of those were not attracted by the magnetic or influenced by the magnetic field.
Let's go to a short break now. Remember, if you are struggling and you need help, remember to post your comments and questions on our Facebook page, facebook.com/LearnExtra, or on Twitter @LearnExtra. Don't go away. We'll be right back. Welcome back, guys. Let's get into some more revision.
If we turn across here, I've got some ice, water, and I want us to have a look at the temperature. The temperature on this, if I read it correctly, is just above freezing. It is at 2 degrees Celsius. Okay, and that is, you can see some very cold water, pretty much stabilized there. And this one I've got quite close to boiling. We've got our flame below, and this one is currently at about 78 degrees Celsius. What I want us to investigate is that we're going to investigate, I want to head back to the board. Our investigation, and hopefully you can go through this yourself, is to investigate what happens when ice melts. We're going to start with glass and with some ice in a glass beaker, and we've got that going. Use the thermometer to read the temperature every minute, and then draw a graph of what's happening to the temperature over the course of time. Investigate a second investigation, so that could be our number 1 and number 2. Investigate what happens when boiling water cools, so that would be called a cooling curve. Start with a beaker of boiling water, use a thermometer to read the temperature every minute, and then draw a graph of temperature versus time. So what I want to indicate to you is, before we go back to our beakers, is that in order to do this, you would need to draw up a table. So here I've got the time in minutes, and the reason we would do that, or we could have time in seconds, as long as you don't have both in your table. So I would probably recommend even doing time in seconds and converting all the minutes to seconds, because we want to be able to fill in what is happening with the temperature. Now, as you do that, do not write down, please, don't do that, don't do this. Maybe let's go with minutes, and I'm going to just pick some numbers. If I have 1 minute, 2 minutes, 3 minutes, 4 minutes, etc. If you were to constantly write down the minutes, you're wasting a lot of time, because the table is telling us that it's time in minutes. So we never, ever write the units within the table. The units are in the heading of the table, not throughout, because it's just a waste of time. The temperature we're measuring in degrees Celsius, and we'll do that in a moment. And we're going to then draw a graph, and I've got the axes there. So let's head back to our table and investigate here. So what have I got? I've got the temperature of this ice. It's currently about 4 or 5 degrees Celsius. And what you should see over time, if we were to leave this going, is that the temperature stays the same. Remember I said it was about 2 degrees, and we haven't got perfect conditions. Oh, no, it's dropping again. Why do you think it would have maybe risen for a few minutes? And the reason is that I wasn't stirring it. So obviously the sides of this container are slightly warmer because they're being surrounded by a warmer room. And we have got, and so the surroundings would be slightly warmer. But if I constantly stir this container and take the reading, there it's gone back to 2, take the reading. This temperature won't change as the ice melts. It all has to undergo a phase change in order to then start raising the temperature again. And the reason for this is because the heat energy that's going in is going into separating, spreading, causing those particles to move away from one another rather than causing them to speed up. So the speeding up, the higher the kinetic energy, means the higher the temperature. And what you should notice here is that this temperature, this ice has melted significantly since I came back to it, and it's still at 2 degrees Celsius. Now, I guess if we had perfect conditions, it might be measuring at 0 degrees Celsius, but it certainly has stayed constant for the amount of time that I have been here, pretty much staying on 2 degrees Celsius. So what I would go and tabulate is after 1 minute, if I was timing this perfectly, which I'm sure you could certainly go and do, it should remain at the same temperature until all the ice is melted. Let's have a look at this one. This hasn't gotten to boiling yet, unfortunately. It was boiling and it's now been cooling. So I think what I'm going to just do is move this one across and heat up this ice slightly. And hopefully what we should see is that it stays at 2 degrees Celsius constantly. Thank you. Hold on, the flame is not really, it's kind of there, but not really doing a huge amount. Let's try and light that flame up some more. It's almost there, but not quite. If I try and heat it again. That's just going, but I don't know how much we can get in terms of heat. What I want you to recognize, though, is our ice has melted, a large amount of the ice has melted, but the temperature, even though the temperature of the room has been much warmer, the temperature of this ice has not changed. It's still 2 degrees Celsius. I'm going to leave that for a few minutes. It has been heating slightly, but as I mix it again and stir it again, it's actually just risen up to 5. But once again, that is because I was leaving this alone and not stirring it. And once again, the temperature is dropping back down. It's currently now 4, and it's going to get back down to 0 degrees Celsius. Okay, let's turn and see one or two more questions based on this. If I turn to question 2, and this would be what a graph would look like based on the practical we've just been investigating. During an investigation into water and its properties, Precious took some ice cubes. So she started with ice cubes, placed them in a beaker and heated them over a burner. She then took the temperature over regular intervals and drew a graph from these results. The graph is shown below. So let's have a look at what this graph is telling us. We've got a temperature going from A to B. Temperature is on the y-axis. And what I want you to notice, and time is on the x-axis, what I want you to recognize here is when you're asked to draw a graph, always you have the independent variable on the x-axis and the dependent variable on the y-axis. And as you look at this graph, I want you to recognize that there are some horizontal sections, some sections where the temperature is not changing, even though this thing has got energy coming into it. We didn't switch off the Bunsen burner. The Bunsen burner was going continuously, but the temperature leveled off. And that would relate to a phase change, when something is changing from a liquid, or in this case it's going from a solid to a liquid, and then a liquid to a gas. So these horizontal sections from B to C and A to D are always going to relate to phase changes, and you would have to consider the context of the question in terms of answering these. Very, very important to identify that the temperature does not change when there is a phase change.
Let's go to a short break now. Remember, if you are struggling and you need help, remember to post your comments and questions on our Facebook page, facebook.com/LearnExtra, or on Twitter @LearnExtra. Don't go away. We'll be right back. Welcome back, guys. Let's get into some more revision. Over to you.
Thank you so much. We are really, really looking forward to this. And as I said to you, chemistry, in terms of all the bonding that you're going to ever do, chemical reactions, it's so vital that you make sure that you have a very, very good understanding of electron configuration. So let's get into it. Electron configuration in the periodic table. This is a simple periodic table that we've got in front of us. What we're going to be learning today, we'll be focusing on drawing electron configurations. So by electron configurations, I'm looking at how electrons are structured around atoms and various models or pictures that help us to understand those. Show that elements are arranged in increasing atomic number on the periodic table. Link the arrangement of the periodic table with atomic structure. Link periodicity, which means the repeating patterns of the table to the various chemical properties of the elements, and learn about trends. So let's get stuck into electron arrangement. Electrons are found in energy levels, and when we say energy levels, we're thinking those ones that are closest to the nucleus will have the least amount of energy, and as the electrons are found in energy levels further away from that central nucleus, they will have to have higher energy. They would be moving in regions of space that are called orbitals. Now let's just take this little bit away so that you can note this very important word, orbitals. Orbitals are regions of space where an electron could be found. There's a higher probability of an electron being found there. They are not spherical rings or different shapes, but they are clouds, electron clouds where electrons could be found. There are various ways that we can represent electron configurations, and we're going to discuss 3 of those today. We're going to look at a concentric circle model, a Lewis diagram, and an Aufbau diagram, and this is also called an energy level diagram. You could very easily in an exam question be asked to draw these models, and so not only are they important for your understanding of bonding and everything else that's going to come in chemistry, they are important in just in terms of answering exam questions. You will be asked to draw these. So let's start with the simplest, the concentric circle model. For the concentric circle model, we are considering energy levels with the electrons found on those energy levels or in those energy levels as circles, concentric circles. And in the first ring, 2 electrons can be found. In the second ring, 8 electrons can be found. And in the next ring, third ring, 8 electrons can be found. And we're not going to go much further than that. So let's have a look at how this would be done. I've got an example here of neon. Neon has 10 and a number 20. What do those numbers mean? We spoke about this last week. The 10 represents the atomic number, okay, which means the number of protons, positive, okay. The 20 represents the atomic mass, and I'm going to change color to indicate that it would be atomic mass. And for atomic mass, you are thinking that is the protons and the neutrons. As we have a look at that, if it's got 10 protons, for this atom to be neutral, if it's got 10 protons, how many electrons must it have? Well, for it to be perfectly neutral, it should have 10 electrons as well, so that overall the charge is 0. There is no charge. So let's go with this atomic model and fill in the electrons. We're going to fill them in as little circles. I said 2 in the first, so 1, 2 in the first. Now we go 8 in the next, so 1, 2, 3, 4, 5, 6, 7, 8. Check with me quickly. Is that a total of 10? We've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. A total of 10 electrons shown in those energy levels. Now, the reason I've shown this one to you specifically is because I want to indicate to you how to arrange them. The electrons I want to recommend is that you put those electrons on the compass points as you work your way around. It's going to be very helpful to you because it's going to show how many spaces there are available for bonding. And we often use something called the Octet Rule, which is saying if you've got filled outer energy level full of, in this case it would be 8, and apart from helium, which has only got 2, so it's only the 2 in the central ring would be filled. If it's got this filled outer energy level of 8, almost like 8 people sitting around a table, there is no more space for any electrons. So there's no need for that atom to bond. And neon actually is one of those noble gases. It doesn't bond with anything else because it's got a stable electron structure, a filled outer energy level. So we've got 2 key words that I want you to note: valence electrons and core electrons. What do you think the core electrons would be meaning? The core electrons must mean the inside ones, right? So the core electrons in this case would be neon's 2 core electrons. They would be ones that are found in the inner energy levels. Whereas the valence electrons, that was the core, the valence electrons are those that are found in the outermost energy level. We're going to use those 2 words a lot as we discuss electron structure. Let's move on to the next, a few of these in terms of practice. Now I've included here Lewis diagrams. Now Lewis diagrams are even simpler than the concentric circle model because they only consider the outer ring, the valence shell, which is helpful. So only valence electrons are shown as either dots or crosses around the symbol for the element. Let's consider carbon. Now you're going to need to know how many protons carbon has so that you can work out how many electrons carbon has. So I've got a periodic table. Let's reference it quickly. Find carbon. Carbon is over here, number 6. That 6 is the atomic number or the number of protons. So we can go back and write carbon and note it has 6. So let's try out this practice the original one where we did the concentric circle model. So I've got 2 rings that I'm drawing and we're going to go 1, 2 in the first, and now I'm suggesting you work with compass points as you go around. 1, 2, 3, 4, 5, 6. So it's got 2 core electrons and 4 valence electrons. Now for this Lewis diagram, we only need to draw the outer ring, the valence electrons, because those are the ones that are going to be involved in bonding, involved in interacting with other elements. So for a Lewis diagram, we're going to just draw, and I'm going to use little crosses to indicate those 4 valence electrons. Let's go on and try another one we're going to work with oxygen. So I'll change pen color, and let's work with yellow for oxygen. Oh, that was, I think, a little bit too far. Let's find oxygen again. Oxygen, let's draw its valence electron, the ring structure, and I need to go to a periodic table, find oxygen. We've got oxygen over here, oxygen number 8. So atomic number, and I'm going to write up here 8 protons, 8 electrons, because overall it's an oxygen atom, so it must be neutral, no overall charge. Let's go. If we've got to make 8 electrons, 1, 2, 3, 4, 5, 6, 7, 8. Now, as I suggested to you, you want to work around on the compass points because it's going to help you to identify where there are spaces for the substance to bond. How many electrons would it gain or lose in order to make sure that it gets to a filled outer energy level? So let's have a look for oxygen here. And we've got oxygen. It's got a lone pair and another lone pair. These guys is what I'm going to call a lone pair. They have paired up already. But notice there is space, 2 separate spaces where oxygen can take up extra electrons. And so usually when oxygen bonds, it's going to form an O2 minus ion. We'll come to that in a few weeks as we look at bonding. Let's keep going. The last type of model I need to look at is sometimes called an Aufbau diagram or an energy level diagram. Now these tend to be the most complicated, so let's spend some time working on those. Aufbau diagrams have these little box structures where we have not just energy levels, but the shells in which, or the orbitals in which those electrons would fit into. So you have a 1s, a 2s, 2p, 3s, 3p, 4s, and it can continue. This first band is the first energy level. The next band is the second energy level. The third band, the third energy level. But in terms of filling up, we're going to always start from the bottom and fill up with electrons. Now, the electrons are shown as little arrows going up and going down. The reason going up and going down is because those electrons, in order to not have a significant repulsion, they are always aligned with opposite spin. So the one spins one way, the other spins the other way. Okay? Now, there are a couple of rules that we need to follow as we work through Aufbau diagrams. Each orbital or little block can only hold 2 electrons, called an electron pair. An electron will always try to enter one with the lowest possible energy level. So you're going to start from the bottom and work your way up. An electron will occupy an orbital on its own, because remember, these are electrons, and so they're going to, if they have the same charge, repel each other. So they will start with their own space, and then, if necessary, they will pair up. So an electron would rather occupy a lower energy level with another electron before occupying a higher one. If it has to, it will pair up. In other words, with one energy level, electrons will fill an s orbital before starting to fill higher up p orbitals. And the s subshell can hold 2 electrons, while the p subshell can hold a maximum of 6.
Let's go to a short break now. Remember, if you are struggling and you need help, remember to post your comments and questions on our Facebook page, facebook.com/LearnExtra, or on Twitter @LearnExtra. Don't go away. We'll be right back. Welcome back, guys. Let's get into some more revision.
We're going to start with some questions on Aufbau diagrams. Remember, they could be asked as energy level diagrams, because as you have a look at it, and I've started with the blocks there, these bands are showing the various different energy levels that a substance would have. So we've got a start with nitrogen. They're asking us to draw an alpha diagram or an energy level diagram for nitrogen. Now, across to your periodic table, find nitrogen. I'm going to need to just clear these so that we can see, because nitrogen is down there. Nitrogen in the middle, 7. Let's go back and start working with nitrogen. It is 7 and 14. And let's just write that again. Nitrogen 7, 14. 7 meaning standing for 7 protons, and for this thing to be overall neutral, it must have 7 electrons as well. Now, if we've been asked to draw these 7 electrons, let's go to an alpha diagram and write them in. Across here, I've already got the blocks drawn. Sometimes that takes a bit of time, so I've already got them drawn. That would be 1s, 2s, 2p. Now, I could draw a little dotted line here to indicate to you that this is the first energy level, that is the second energy level. The second energy level has 2s and 2p. Now, I didn't speak to you earlier about what those mean. The s is standing for a spherically shaped orbital. So almost like a ball, those electrons have a sphere in which the orbitals is shaped in. The p is a very interesting shape. It's like a figure of 8, or a almost like a dumbbell-shaped figure, and it goes up and down. You'll notice there are 3 of them: up, down, left, right, and forward and backwards. So these 3 or p orbitals together can carry 6 electrons. Let's fill in the nitrogen, and I've got these boxes. Remember, I've said to you we start from the bottom and we fill in. So 1, opposite spin, 2. That whole s orbital, that whole first energy level is now full, so we have to go to the second energy level. The next one, 1, 2, so 1, 2, 3, 4, 5, 6, 7. That is the 7 valence electrons, the 7 electrons for nitrogen. Now let's have a quick look at it and identify that as I drew these in, I didn't put the 2 of those in one of the p orbitals. I separated them out, putting 1 in each of those p orbitals, because they want to be as far away from each other as possible within that same energy band. So coming back here, how many valence electrons does nitrogen have? Well, valence, remember, by valence I'm speaking about those outer electrons, and it would be everything in this top energy level. So 1, 2, 3, 4, 5. 5 valence electrons. And nitrogen can make 3 bonds, because if you look at it, it's got 3 open spaces waiting to bond. Let's turn down to another one. We've got it there. And let's look at a different one. This is for oxygen. And oxygen, I'm going to come back. We've used oxygen a few moments ago. It was oxygen 6. So let's write it up. Oxygen O had 6 and... oh, I don't think it was 6. Just check me quickly. I think it was 8. Oxygen. I was looking at carbon for a second there. We are considering oxygen, which is 8. So going back here, this should be oxygen 8 and 16. Specifically going back to the question, and I've thrown this question into you almost as a bit of a curveball, because I want you to think about it. They have asked us not for an oxygen atom, but for an oxygen ion. Now, an oxygen ion's formula would be O2 minus. The reason it's going to be 2 minus is because it's gained or taken up an extra 2 electrons, and that's vitally important. So as we draw it, we're going to have 8 protons, but if there must be an overall 2 minus charge, how many electrons must there be? Well, overall 2 negative, so it must have 2 more, so therefore 10 electrons. Are you all happy with that? Let's come across and fill in our Aufbau diagram. So 1s, 2s, 2p, and we're going to fit these in. So in the first, 1, 2. In the second, 1, 2, 3, 4. Count so long. 1, 2, 3, 4, 5, 6, 7. Now we can start pairing up. 8. Are you happy that that would have satisfied the 8 electrons that oxygen originally had? Now, if it's taking up an extra 2, where are those extra 2 going to fit? They would be here, 9, 10. So overall, this oxygen atom has gained an extra 2 electrons, and so is overall 2 minus. You must be able to do these for ions as well as for atoms. And if I would recommend to you, as you work through these, and I've made a quick note here, if you're asked to draw Aufbau diagrams or energy level diagrams for ions, I would recommend draw the original atom, as I did. Then consider, if it's positive, it must have lost electrons, because it has less electrons than protons. The proton number is outweighing, so it must have given away or lost electrons. Whereas if that ion is negative, then it must have gained or taken up extra electrons. Remember, electrons, although we're adding something, we're adding extra negatives. So it's taking up extra negatives, and so you would be able to fit those in on your Aufbau diagram. Usually when things are bonding, they are trying to make sure that that energy level is full. Okay? So if they're giving away, it's normally giving away 1 or 2 from the outer ring, so that what is left behind has a filled outer energy level.
Well, guys, we've come to the end of today's show. Thanks for joining me. Remember to visit our website, learnextra.co.za/live, to get the notes and to watch the videos. And if you are stuck and you have any questions, send an email to helpdesk@learnextra.co.za and we will help you. Also, guys, we are dedicating the month of March to Library Month. Join us as we discuss some great books and some exciting competitions on the way. Goodbye.